for reminding me. I think that part is missing on your record, but again, that I have given that introduction. It's not necessary to say much more things there. But this is your time. You can raise, ask any questions. But from the beginning, you can start everything until you become a digital circuit designer. What is needed? Nothing needed, because we are doing all these things from the scratch. Okay. Then what is the section we are going to cover? That is digital electronics. Anyway, that if I write this one is digital electronics, we are going to cover, but we have only six lectures, and we are going to spend here 12 hours. During that time, we will try to do maximum, and not only the circuit designing part. Can you excuse me for a moment? Sorry for the disturbance actually. We're going to do this digital electronics, but the entire digital electronics we are not going to cover. But other than the circuit designing and some of the aspects, some of the major important parts we are going to cover during this 12 hours period. But anyway, when it comes to this subject, digital electronics, what do you know about this? Basically, your answer may be, sometimes it may be zero. Sometimes some of you might know about certain things, and some of you might have much more experiences with this. But anyway, what do you think about this one? I ask this question in different way. What do you know about this word digital? Where can we find this? Have you heard about this word? I think answer may be yes. Yes, I think many answers are coming in laptops, computers, phones. Yes, digital. We have digital phones, digital computers, digital laptops like that. Many products are there. Those products are digital products. And I think a lot of products surround us. Those electronic products are digital products. What do you think? Do you like to use those things? Do you like to use digital products? Do you like?
Of course, sir.
Then if I ask another question, that if the answer is yes, why? Now I'm asking one question, do you like it? Then if you like it, yes, then why? Okay, shall I check the chat? There you have, okay, written, it make life easy to read. Makes life easier. It speed up things, entertaining, easy to handle. That's a reason that weekdays, if you are going to do this type of lectures, that's all the time. This is some, sorry that I. Hello, morning. I think there we can. Okay, shall we write that the benefits or maybe the advantages, so maybe you are receiving from these digital products, then you have mentioned then easy to use, then many features, and it gives much more things to us, and for the correct purpose, then I think we can say high accuracy and efficient, easy to read, and all these things we can say easy to use them. What else? Purpose is to so many options. Yes. Many options and user friendly. Okay. For the moment, I think this may be enough. Okay. Then I think when you see these things and makes communication easier to a certain extent, like getting in touch with people abroad, saves times as it reduces time taken to physically do things. Okay, then all of you have written certain things in positive manner. Okay, I didn't see any negative comment here. Okay, then with these digital products, with this the make availability of all these digital products, what we have realized that many things in our life, it may be easily we can do the things because of those features, because of those advantages, because of these benefits. We like to use these products. Okay, then when we consider the counterpart, the other part of this one, then analog products, little by little, at most of the time that we, if it is possible, we are trying to replace those analog products. For example, that I think you don't have experience with these things. Maybe a couple of decades ago, we had analog mobile phones. It may be something like a brick. Okay, we can kill a person other than taking a call. Okay, then I think maybe some of you might have seen those things that you had your CRT kind of TVs in your living space, but we have replaced those things with LCD TVs and other things like that. Okay. Okay, sorry. Then I think then we have realized that because of these things, because these features, we like to use these digital products, and actually we like to use all these things because of so many benefits, so many features, and we have experience. Then with the analog things, all the time, if possible, we try to replace those things. Why? We have seen that many features are there, many advantages. It makes our life easy. Because of that, we are going there. There is no problem going there. But what is the secret behind this? How these digital products are doing this magic? What's secret behind this? Some kind of the features may be there over the analog counterpart, but these analog products are not having that one. but these digital products are having that. What is the secret? So that's what we are going to discuss here. That is our starting point of the lecture. And actually, these products are based on logic states. Logic states. When we say logic states, it's actually two logic states. The starting point of this digital electronics, this logic state, the implementation and all these things are going maybe like it's going towards that World War II. Okay, during the World War II time, then the United States Navy, they have developed this system. Okay, but actually that they had a not two-state logic, they had a 10-state logic. Why is 10-state logic are there? Because it was 10-state logic. Why? To match with decimal number system. Because with decimal number system, we have 0 to 9, 10 digits. To cover that one, they had 10-state logic. But realizing that the maintaining of this 10-state logic is a really, really difficult one, we have reduced that one into two-state logic. But maintaining of this two-state logic is a difficult. Then having that difficulties, then how can we maintain 10-state logic? But still that US Navy people, they are using this 10-state logic circuits with their systems. But all over the world, other than them, then we are using this two-state logic circuits. Okay, then two-state logic, then that is the first thing we have to realize, this one, two-state logic. And with this two-state logic, what do we have? It may be high, low. It may be true, false. Okay, it may be on and off. Like that, we have two states. You have to maintain this one, two state. These are the logic states. Then next thing, actually, after identifying this one, after understanding this one, then we have to build up the circuits based on these two-state logic. Actually, that is the secret behind this one. Because of this two-state logic, it's a very simple. It's a very, very simple to design a circuit, how to handle the circuit, and all these things are become very simple process. That's why all the time, if it is possible, we are replacing these analog things by using these digital products, by using these digital versions of those things. Before we go a little bit further, can I ask one question again? One day, do you think that can we replace everything there? And can we put all the digital circuits, digital systems there? Can we convert everything into digital? What do you think? Yes. Okay, it's good that you have mentioned no. Then second question, why no? Yes, because the nature is analog. Because the whole world is analog. We are analog. Everything here, so when you look at the outside of your window, you can see that wind is blowing, the trees are waving, birds are flying. All these events are analog. And we cannot replace everything digital, all these things, but whatever the thing that we can see in the digital world, those are very good things. Then we are visiting there to the digital world, then do whatever the thing we need, then come back. Okay. Then basically the whole world is analog. What about your parents' love? Is it digital? That is analog. Your one may be digital, but anyway, then many things are there surrounding you. Those events are analog. Because of that, we have to go to this one. For example, you are with your mobile phone, you are talking to your friend. But how can you talk in digital form? No, your voice is analog. The mobile phone is picking your voice and convert it to the digital, and with this all these digital features, it sends it to the other place, to your friend's place. Then his or her mobile phone will convert this digital signal into analog and make available that one to the understand signal. Then this is a real world scenario, and this, because of this, we have to experience this digital world. But anyway, all these things have to be finally, if we are the user, if we are the human being, maybe the live being are the users of these systems, we have to go with analog systems. Okay, then come back to the lecture again. Okay, then understanding all these things, that the logic state is the secret behind this. Okay, how can we make circuit? Yes, robots are also digital products. They are doing everything digital. And sometimes that we need some kind of analog interfaces there, but anyway, everything is digital. Okay, then how can we make digital circuits? Saying that all these things are based on two-state logic and everything, and they are very simple like that, saying like this. How can we make these circuits? Okay, to do that, we have to collect many tools. One thing, first thing, we have to find a number system to be matched with our two-state logic. What are the number systems we know? Number systems, the decimal number system, we know that this is our day-to-day number system. They're using decimal number system. With decimal number system, what is the base? Base is 10. And what are the digits? Decimal digits, it's 0 to 9. Okay, what are the other number systems you know? The octal number system. Decimal number system, I think we can write these numbers. Then it may be. Okay. Two, three, four. It's decimal. Okay, we can say the base here, and maybe you can say 9, 7, 4, 5, 7, 5, like that. This is 10, or may you can say 9, 4, 7, 5 decimal. What are the other number systems you know? This is decimal number system. What about the octal number system? Octal means that then base is 8. Then what are the octal digits? 0 to 7. Then what are the numbers you can write using octal number systems? Then if you write 2, 3, 4, then base is 8. But you can't use that number 8, 9 like that. Then 1, 2, 5, 7. That is okay. Then 1, 2, 5, 7. If you use this one, then you can say it's octal. Using this letter O or the number 8, you can indicate that this number system you are using is octal. Now what else? Then binary number system. Then what is the base? Base is 2. Then binary digits 0 and 1. The numbers you can use, numbers you can write. It's 1 0 1 1 0 2. It's 1 1 1 0 2. Or maybe you can write 1 1 1 0 binary like that. Okay, here this binary number systems are we don't say binary digits. Instead, we say it's bits. Okay, then we can say bits. 0 is a bit, 1 is a bit. Okay, what are the other number systems? You can, and another one is hexadecimal number system. Hexadecimal number system, then base is 16, then digits hexadecimal digits are 0 to 9 because we need 16 digits. Then 0 to 9 we can use, and from the alphabet A to F. Then altogether we have 16 digits there. Then what are the numbers? We can see the example numbers. Then 3, 4, 5. Base is 16, and 3C, 1A. Base is 16. Then 3C, 1, 6. Then you can say hex. Now, what we have done here, then we want to have the number system. Then number system, that is what we have collected so far. We know the logic states, the number system. We selected the binary number system to be used with our two-state logic. Then what else do we need? Next thing we need, that is, we want to do some kind of mathematical calculations. Then we need some kind of arithmetic operations. Then our normal arithmetic operations, we can't use this with this two-state logic. What are the normal arithmetic operations we are doing in our day-to-day life? Addition, subtraction, multiplication, like that, we are doing those things. But those things we cannot use there directly. Because of that, we have to have some kind of arithmetic operations matching with this two-state logic. Then where can we find those things? What are those things? Then we can learn something from another kind of world. Actually, that when you consider the Boolean algebra, it's some kind of world. But actually, we are not going to learn Boolean algebra here. If you are going to use Boolean algebra, it might take more than 2 years. But we are taking some kind of concept from this Boolean algebra. And one is Boolean variable. So we need Boolean variables. Anyhow, whatever the system we are going to make, we need variables. But when I say it's a Boolean variable, the Boolean variable is special. Why? The Boolean algebra, the entire Boolean algebra is based on true-false logic. The true-false logic we use in Boolean algebra. Then when it comes to Boolean variables also having that nature. Okay. If I take Boolean variable A may be true or A may be false. Okay. We can directly map this one with our requirement. We can say true is 1, sorry, because matching with binary number system. I couldn't mention it here. Because here we can take a binary number system, but we have this true false kind of things. Then here, how can we match our thing with binary number system? When we have true or maybe on, maybe high, we can say it's 1. When we have false, off, or maybe low, we can represent all these states by using 0. Then that's why we are using binary number system. There also we have 2 digits. Then using these 2 bits, we are going to represent those. Then this true, false, this one, we can map. This is 1 and this is 0. When we say that A is true, A is 1, we say that is A. When I say that A is false, A is 0, we say that is A bar. Okay. Then A is 1, we can say that is A. When A is 0, we can say that is A bar. It's just a notation. But same thing for B, C, D, like that. You can have any number of Boolean variables, but those things you say that you have this 2-state logic, maybe 1 or 0. Then for that one, hereafter, to represent those things easily, we have this notation. When A is 0, we say it's A bar. When A is 1, we say it's A. Okay. Then we are taking some concept from Boolean algebra. One is Boolean variables. Okay. The other one, can we match Boolean algebra only with binary? Yes, actually, at the moment that we can do this one with binary, because that when you match this Boolean algebra with binary, it's easy. Why? With binary also we have 2 state. In Boolean algebra also we have 2 states. We can match this one with some other number systems also, but there may be some kind of conversion needed. But without having any conversion, we can directly use this binary. Okay. Then Boolean variable and some kind of that logical operations we need. We are taking that one is from Boolean algebra is logical operation. Those are the Boolean operations. Okay, we can say it's Boolean operations. When I write those Boolean operations, then you will realize that those things you already know. Those are the things that we're going to take it from there. That is Boolean operations. Not O and exclusive O. These are the 6 basic operations we are going to take from Boolean algebra to be used with our circuits. Okay, then actually what we are going to do, that here we are going to use this logical operations to make circuits. The final aim is that we want to have a digital product. To make digital product, we want to make digital circuits. Then how can we make digital circuits? Then we know that we have two-state logic and we have this binary number system, and we have taken some kind of logical operations from Boolean algebra. Then with Boolean algebra, we can do this not operation, no operation, and operation like that. But to really implement those functionalities in practical manner, we need some kind of circuits to do this operation. Okay. Then we are making some kind of electronic circuit to do these logical operations. We call those things logical devices. We need some kind of devices to do these operations. And those is logical devices. Actually, if I put a different name, then you will know that they are logic gates. Okay. I think some of you might know about these logic gate devices, but anyway, we'll start it from the beginning and we can start to learn about this logic. Okay, then we can start from this. This what is first logic gate we are going to learn? That is not gate. Okay, most of you have, I think, know about these things, but to have a complete note, quickly we follow this one. I think some of you might not know about these things. Then considering that some of the people, some of the students, and some of the friends of your friends already don't have about this type of knowledge, we can quickly follow these things. Okay, not gate. When you consider any kind of digital circuit, gate, or whatever the thing, we need three things there. One thing is symbol. We need to have symbol, then notation, and truth table. Okay, the symbol for this NOT gate is this. The symbol, it has single input and single output. The notation is a bar. Whatever the thing we are giving here, it gives the inverted version of it. The truth table is, we have only single input with NOT gate. This input may be, you know, that 0, 1, it can take. When you give 0, the output is 1. When you give 1, output will be 0. Okay, next gate. That is O gate. Then O gate symbol is something like this. But remember that O gate needs minimum 2 inputs. What is maximum number? Theoretically, there is no limit. Okay, but minimum is 2. Maximum, you can go up to any number. Theoretically, but practically, we don't have that type of things. But the notation is here, F equals AOB. AOB we write using this plus mark. Yes, lecture recording. Yes. I'll upload the lecture recording because I know you are asking that lecture. I'll upload those things. I think I haven't uploaded your circuit theory lectures also. Have I? I'll upload those things also. Then after that, I'll send the link to you. Can you write on the chat one of your batch representative email address? Then I can send the links to her, he or she. Then it can be shared after that. Then truth table here, we have two inputs. These are the possible combinations. With OR gate here, but the function of this OR gate is if any input is 1, output will be 1. Third one, AND gate. AND gate also minimum, it is necessary to have 2 inputs. Maximum theoretically there is no limit. The notation is A dot B, or you can write without having dot also. Truth table for this one. Here 0. Here one input is 1, but it does not give output. Here another one is 1, but both inputs should be 1. Then only and gives out. That it's better to check that the meaning of these two gates. These are the two important gates we are having. Very, very important gates. With O, what is we are having? When A, O, B is there, output will be there. When A1 or B1, output will be 1. With AND gate, completely different. Both should be there. Then only we can have 1. Then if you want to check both things are true, both things at the same time, then your solution should be AND. But if you want to check one of these things are true, then if you want to check one of these things, then the solution is O. Okay, then next one is not a new one, but again, the fourth one is no gate. It's a combination of O and NOT, but this is O gate and this is a negative version. Is F. The notation is this is O and we are putting on top of that bar, then it will become no. The truth table is completely opposite of O gate. For all the cases with O gate, we have one output for these 3 combinations, but here it's 0, 0, 0, here 1. Okay. But actually, no gate is a combination like this. We have this no gate and in front of that we have not gate. We have combined these two together. That's why this small circle in front of this one indicating that's not operation. Okay. Fifth one is NAND gate. NAND gate is, as usual, you know that the opposite of AND gate. The notation is A dot B bar, or you can write it without dot also. The truth table for AND you have 1 here, then this should be 0. All other three cases, all other three options that we have 1 there. Okay. Last one. Exclusive OR gate. The circuit symbol is a little bit different here. The notation is this is the way A exclusive OB. It's quite different truth table we can see here. 0, 1, 1, 0. What is this? It gives us a different functionality. That is that when our inputs are different, it gives 1. When our inputs are same, it gives 0. Okay. Up to this point, are you okay? Okay, Dhanuka, thank you that I received your email address, that after uploading those things, and I'll send you the link, then you can share with your friends. Okay, now actually so far we have collected whatever the tools and whatever the things and we needed to design circuit. Okay. Now what we have to do next? Next, we have to start designing circuits. Are you ready to do that one? We have come to that stage a little bit early. But before that, can you have a small exercise? Okay. Then okay, not gate, and one of your requests came to see the not gate again. Okay, this one. Okay, this is not gate, and this is O. This is N, and no. This is NAND. NAND is also a combination of AND gate and not gate. Okay. Whatever the exercise that we are going to do here is that we can say exercise maybe first one. See this and whether you can do it or not. Okay, I have a Boolean variable A. This is the one input I am taking. Okay, I am sending this one through a NOT gate. Then what is here I am receiving? It's A bar. Okay. Then I'll take another variable, that is B, another input coming from different place. Okay, then I'll bring it here. I take AND gate. And I input this one here, this one here. Then what is the output of this gate? The function of this gate is to take whatever the two inputs and take the AND operation between these two inputs. The first input is A bar, and it will take AND operation between A bar and B. Why? This is the one input and this is the other input. Then it will take AND operation in between these two. Okay. Then I can take another one. Now see. Okay. If I send this one through this not O gate, then what is the output of this O gate? What is here? It's A bar B is the one input. This is C is the other input. It has to take operation in between these two. You have to consider this A bar B as a single entity. Now, after coming out from this gate, is not two separated things. A bar B bar separated is not. A bar B bar is a one entity. Then from this gate, what do we receive? It's operation between A bar B and C. Is it okay? Now spend a couple of minutes, try to understand this one. Is it okay with you? Can you do this? Okay, good one. Yes. I'm receiving yes answers, and if I receive no answer is also, I would like to see that one. Okay, I think how many of you have connected here? Maybe 106 participants are there. Okay, I don't expect 106 yes, but anyway, that at least that if you type many years, that generally I can understand that most of you have understood this one. But anyway, it doesn't matter that I am going to discuss it with you. But see that one, is it difficult? What do you think? And we have three variables. A is going through a NOT gate, then it's after that it will become A bar. Then A bar and B is going to through this gate and gate, then it will take AND operation in between those two. Then after that we use O gate, then this is the final result. Okay. Then shall we try another one? Okay, I'll draw this one. You can try it. We have three variables again. C, and I take AND gate, this one, and I take another AND gate. Okay, how can we do this one? I think it's not a challenge, and this is the input here. This is A and this is B, then this should be AB. And from this one, this is B, this is C bar, then this is BC bar. And here you have BC bar and AB. Then output of this one is AB plus BC bar. Okay. Then this is from this one, we can have AB here. This is AD. And this one, this is B bar. This is one is C exclusive. Sorry. B bar. Okay. And this is AB, AD, and this one AB plus AD from this point. And this one is C exclusive of B bar. And this output here, this is AB plus AD. And the other one is C exclusive of B bar and no. If you want that, you can put bracket here also, but it doesn't matter that bracket is there or not. What do you think? Is it okay? These three? Okay. Then if you're okay with this, then what about the opposite of this one? For example, if I write an equation like this, F equals A bar B plus A B C bar. Can you draw a circuit for this one? Shall we try this one also? But now when you have a circuit that you can write output Boolean equation here. Okay. Here you can write for this circuit, you can write output Boolean equations. Then shall we try that when you have an equation, is it possible to draw the circuit? maybe this one, A bar, B bar, C. Then this is this one, and ABC. Shall we draw circuit for these things? Okay, shall we look at this one? Make this thing first, and we need three variables there, starting from A, B, C. We need A bar here. And shall we make first term? This is A bar B. And we have to make B bar C here. B bar C. Then we have to combine with A. Then from this point, we have A, B bar C. Then here we have A bar B. Then after that, we can combine this one. Then finally, we have F A bar B plus B C bar. Okay, this one. We have three variables A, B, C. And we want to make A bar, B bar, C bar also. First, we make these three things. A bar we have now. This is B bar. And this is C bar. First, we make this term. A bar, B bar, C bar. A bar, B bar, and C. This is A bar, B bar, C. And we make this one. Here we need A bar, B, and C bar. This is A bar, B, C bar. Okay. This one A, B, C. We can take A, where is B? Here we have B and C. C is here. This is A, B, C. Okay. Then we can take In this point, we have G. Okay, question is that there is a particular way we draw the wires, or we preferred way is fine. Okay. Actually, there are two ways of drawing these things, but let me finish this one and I'll draw it at the end. This. We have three variables here. Sorry, four variables: A, B, C, and D. And D. We want to make B bar. Here we have B bar. Okay. Shall we make this exclusive O1 first? This is A. This is, and we need another 3-input OR gate. To make this one, here we can take A, this is B bar, and C. This is A plus B bar plus C. Okay, then we have to take another one. To take this C bar D. Sorry, this is C D bar. And after that, we need another AND gate to combine this one and AB. A is here. Where is B? B is also here. And this is A, B, C, D. Okay. This is the last one. We need A, B, C, D again. We need B bar, C bar. We can make this B bar, C bar here. Then try to make this first one. Okay. Then if you don't have any question, then actually to draw the circuits actually for this connected and not connected things. But here in this case, I used this notation. When you have wires crossing like this is not connected. Okay. But when you have wires like this, with this dot, it's connected. Okay. The other convention, maybe the previous method we have used, this is the old method we have used, is if it is not connected, then you have to jump over the wires. And if it is connected, just crossing. But you can see that this is method 1. This is new method. Actually, it's not new method. A couple of decades back, they introduced this one. This is method 2, old method. But whatever the method, you are free to use this one or this one, but not both things are together. Why? But here, if you have a connection like this, it's not connected. But the method 2, if you have this crossing like kind of things, that is connected. Then don't mix two things together, but you can use whatever the method you like. But here I use method 1. All the time when there is a dot, it says there is a connection. Okay, anything else? I think today all the necessary things we have collected, and you know that how to draw a circuit when you have a Boolean output equation. And when you have a circuit, you know how to write output Boolean equation also. Both ways you know now. And so far, at the end, if you know all these things, that is what we expected from the end of the day 1. But next day, definitely you can start designing. Actually, now you have become a digital designer, but you have to have hands-on experience to do that one. The skills we have to develop. Okay, next day we can do it. Anything, any question? This is 7. And this is 6th one. Okay, this is 5th one. If you have any question, this. Okay, if you don't have any question, shall we finish the class today? I think we can have the class next Monday morning, as usual. Until that, be safe. And I think take care of yourself. I think when the country is open, but still the danger is not gone. That danger is there. And think about your family members, you and all the people, and be safe. And thank you very much for your participation, your time, and we'll meet on next Monday. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
You're welcome.
Thank you, sir.